geologic hydrogen could be an amazing new energy source under our feet. And this week, we have a new paper that shows for the first time a map showing where this gold hydrogen might be found right here in the lower 48 states. Let's get into it. I'm here with the American Geosciences Institute. This paper, titled Prospectivity Mapping for Geologic Hydrogen by Sarah E. Gelman, Jane S. Heron, and Jeffrey S. Ellis, was published by the U.S. Geological Survey in January 2025. The purpose of the paper is to provide the first publicly available prospectivity map for geologic hydrogen in the conterminous United States. In other words, they wanted to find out where in the U.S. is there a geologic hydrogen system that may be capable of producing energy. But what is geologic hydrogen? It's also known as white or gold hydrogen. Unlike fossil fuels, burning hydrogen only produces water as a byproduct. So it's considered a zero-carbon energy resource if it's extracted and used properly. But unlike fossil fuels, which have been explored for decades, exploration for geologic hydrogen is still in its infancy. We know that high concentrations of geologic hydrogen exist in a few places around the world, but we aren't sure where else it might occur. That's why this paper is so exciting. This paper is different from previous assessments because instead of focusing on specific locations or prospects, they look at the entire region or play scale. Their prospectivity map shows areas where the major components needed for hydrogen accumulation are likely all present, a source of sufficient hydrogen generation, porous reservoirs for storage, and seals to prevent leakage. Basically, they're looking at the big picture, trying to figure out where geologic hydrogen systems are most likely to occur at the regional scale, so that future efforts can be concentrated in those areas. To make their map, the authors developed a scoring system based on the occurrence of specific geologic conditions that are required for hydrogen accumulation. Each condition was scored from 1 to 9, with 9 being the highest score. Then the scores were added up for each location to get an overall prospectivity score. The resulting map shows that 2 regions stand out as having the highest prospectivity for geologic hydrogen in the United States. First is the midcontinent region, which includes parts of Kansas, Nebraska, South Dakota, and North Dakota. This region is underlain by a thick sequence of sedimentary rocks that were deposited in a shallow marine environment during the Paleozoic and Mesozoic eras. These rocks are rich in organic matter, providing a source of hydrogen. The hydrogen is released through a process called Carrigan cracking, in which the organic matter is broken down by heat and pressure. Additionally, this region has a lot of faults, which provide pathways for the hydrogen to migrate and accumulate. Several geologic hydrogen accumulations have already been discovered in the Rocky Mountain region, and the presence of these structures suggests that similar accumulations may exist beneath the midcontinent. The second region is along the central California coast. Here, hydrogen is released from the alteration of ultramafic rocks. Ultramafic rocks are igneous rocks that are rich in magnesium and iron. When these rocks come into contact with surface water, they undergo a process called serpentinization. During serpentinization, the iron in the rock reacts with oxygen and water to form serpentine minerals. This reaction releases hydrogen gas. The hydrogen then migrates into the overlying sedimentary rocks where it can be trapped. This geologic hydrogen system has been studied extensively along the California coast, and several hydrogen wells have been drilled in the area. Now, even though these 2 regions have the highest prospectivity scores, it is important to note that the geologic hydrogen systems found within them are likely to be distributed over large areas and depths, meaning that extracting the hydrogen will be challenging. It'll require innovative drilling and extraction techniques. Also, remember that this is a regional map, meaning that the geologic hydrogen systems haven't been explored in detail. The map shows where geologic hydrogen systems are most likely to occur, not where they have actually been discovered. More work is needed to confirm the presence of geologic hydrogen in these areas. What's more, The authors caution that their methodology doesn't consider factors such as the amount of hydrogen present, the accessibility of the hydrogen, the cost of extraction, or the environmental impacts of extraction. Those need to be considered when evaluating the actual potential of geologic hydrogen in these regions. Despite these challenges, the identification of these prospective regions is a significant step forward in the exploration of geologic hydrogen. The map provides a framework for prioritizing areas for future investigations, helping researchers focus their efforts where they're most likely to be successful. It also links surface observations of hydrogen degassing to far-field source regions. This linkage is important because it helps us better understand the distribution of geologic hydrogen at the continental scale. Plus, the methodology used to create the map is flexible and expandable. It can be adapted to incorporate new concepts and data as they become available, and it can be applied to other regions outside of the contiguous United States. Overall, this paper makes a significant contribution to our understanding of geologic hydrogen. It is an important tool for guiding future exploration efforts, and it has the potential to help us harness this clean energy source. One key aspect of this paper is the way that the authors define the geologic hydrogen system. They divide the system into three primary components: source, reservoir, and seal. Defining the geologic hydrogen system in this way allows for a more comprehensive and systematic approach to its exploration. Each component is crucial for the formation and accumulation of geologic hydrogen. Let's break down each of these components one by one. The source component includes processes that generate hydrogen. In this paper, they consider three types of subcomponents: serpentinization, radiolysis, and deep sources of hydrogen. Serpentinization, we talked about this earlier. It occurs when ultramafic rocks weather and the iron in the rock reacts with oxygen and water to form serpentine minerals, releasing hydrogen gas. Radiolysis is the breakdown of water molecules by ionizing radiation, such as gamma rays and alpha particles. This process occurs naturally in rocks that contain radioactive elements, such as uranium and thorium. Finally, deep sources of hydrogen are processes that generate hydrogen at depth, such as the decomposition of organic matter. The second component is the reservoir. This refers to the rock formations that can store hydrogen. Porosity is an important characteristic of a reservoir rock, as it provides the space for hydrogen to be stored. Porosity is defined as the percentage of a rock's volume that is occupied by pore spaces or voids. The size of these pores also plays a role in determining how easily hydrogen can move through the rock. Therefore, permeability is another important characteristic of reservoir rocks. Permeability is a measure of the interconnectedness of the pores in a rock, and it affects the rate at which hydrogen can flow through the rock. The third component is the seal. A seal is a rock unit that prevents the leakage of hydrogen from a geologic hydrogen system. The integrity of a seal is important because it helps to maintain the pressure and concentration of hydrogen within the system. Seals are typically composed of low permeable rocks, such as shale, which restrict the movement of hydrogen. It's important to understand the interactions among these components. The source component generates hydrogen, which then migrates through the subsurface and accumulates in the reservoir. The seal prevents the hydrogen from escaping to the atmosphere, allowing for the buildup of hydrogen over time. By considering all three components, geologists can develop a more complete picture of how geologic hydrogen systems form and evolve, leading to a better understanding of where to look for these valuable resources. The U.S. Geological Survey is already working on updating their map of geologic hydrogen using new data and improved methodologies. Hopefully in a few years, we'll have an updated map to share with all of you. And that's all for this week's episode. If you like this series, stay tuned for more. All the best, and see you next time.